Great, so to continue processing our output that we would get when we run a linear regression between coffee sales and temperature. So again, we've been talking about how we have this regression line here, and it's got two things to it. It's got an intercept and a slope. Well, the important thing is we can write this as an equation, and that equation is what we can use to work with to basically predict what coffee sales would be on average at a given temperature. So we write it just like our algebraic line would be, just like you've seen, a million times before in Algebra 1. So just a little bit of stats symbology. I'm going to be really loose with this on grading, so don't worry too much about it. But when we write our regression equation for prediction that has all our numbers in it, we put a little hat over the response variable to indicate that this is a prediction. It's not the actual value of coffee sales. It's a prediction of average coffee sales. So this is saying we predict y hat, number of coffees sold predicted, is equal to the intercept plus the slope times the explanatory variable. And this is our basic regression algebra equation. So this is it. This is showing the relationship between the temperature and the number of coffees sold. This is our prediction regression equation. And again, it predicts averages. Any temperature you plug in here is going to spit out a predicted average number of coffees sold. Okay, on to the inferential part. You've worked with p-values before, and you've even worked with t-values a little bit. So we still have a hypothesis test with this slope coefficient. There's a hypothesis test with the intercept value, but we don't worry about it as much. It's not important at this point. But let me get to this idea here. Remember, we care about the relationship between temperature and coffee sales. So what if there was no relationship at all? Then there wouldn't be anything interesting to say. If there was no relationship between temperature and coffee sales, what would that slope be? The slope would be 0. It would be a flat line. There would be no slope, and there would be nothing interesting to say. We would not find evidence for a relationship between temperature and coffee sold. Temperature would not be statistically significant in predicting coffee sold. So when we run a regression, the default hypothesis test that is being run is that this slope coefficient is 0. That is the default null hypothesis. That is the assumption we're starting from. And based on that estimate of the slope and its error and t-value and all those other things, we get a p-value. In other words, what's the probability that we obtain a sample slope of this magnitude or larger, assuming that the true slope is 0? Well, the p-value is basically very, very small. So our p-value operates in all cases for regression with the null hypothesis being 0, being no relationship, a slope of 0. And as I've emphasized before, the null hypothesis is about the population slope. So from a symbology standpoint down here, we tend to label the slope, at least the population slope too, as beta. So our null hypothesis is that the population slope between temperature and coffee sales is 0, with the alternative hypothesis being that it's not 0. Because the p-value here is really, really small, we can reject the null hypothesis that the population slope between temperature and coffee sales is 0, and that gives us evidence at a very small significance level that the relationship between temperature and coffee sales is statistically significant. We have evidence that temperature predicts coffee sales on average. It's just like with the randomization distribution. We have our null hypothesis, but it's always going to be the same thing here. The population slope of interest between the explanatory variable temperature and the response variable coffee sales is equal to 0. Great. Okay. So this is what our situation looks like. Predicted average coffee sales, that's coffee with the little hat on it, is equal to the intercept, 49,337, minus the slope, the sample slope, 553.7, times the explanatory variable of temperature. And we know that this is statistically significant, that we have evidence that this true population slope between these things is not 0. So we can find evidence for a relationship. Okay, quick little visual check for what the intercept means. Again, the intercept is where the regression line crosses the y-axis, or where the explanatory variable, in this case temperature, is 0. So we go to a temperature equals 0, and we go all the way up to the regression line, and we get an intercept of 49,337. So for 0 degree day, we predict an average of 49,337 coffees sold. Okay, really important thing. It often makes no sense to interpret the intercept. Why? Because for a lot of things we measure, there is no 0 for them. So, for example, if we were to do something with body temperature or pulse rate and predicting a health outcome, if we have healthy living human beings in our sample, we're not going to have a body temperature or a pulse rate of 0 unless our participants are dead. And for a standard healthy study of individuals, that's not going to be the case. For the circumstances where 0 is not within the range of the data of the explanatory variable, we do not worry about what this number means. In this case, 0 is within the range of temperatures. So we can interpret it. We can interpret the intercept. It has some meaning to it. If 0 is not in our range of values for our temperatures, even if we only had temperatures of 30 degrees and up, we would still not interpret 0 because that's extrapolation beyond the range of the data in our sample. And we'll show this in a second. So do not interpret the intercept directly. If 0 is not within the range of the data, it often makes no sense. In this case, it does. What does the slope mean? I've talked about this a bunch. It's rise over run. We think about marginal, incremental, 1 unit changes in the explanatory variable, in this case temperature. So we say for each additional degree warmer or each additional degree increase, we expect about 554 fewer coffees to be sold on average. As that temperature goes up, this line decreases by about 554 units of coffee on average for each temperature increase. Now again, we're using this regression line to make predictions. We want to predict for a given temperature how many coffee sales we're going to have on average. But we cannot do that safely if we pick temperatures outside the range of our data. We do our regression. This is not forecasting. Forecasting is a different thing than basic linear regression. Extrapolation is predicting y values for x values that are outside the range of the data, and it's not okay. The reason is we don't know for certain that this line would logically continue like that. Wherever the line is, we need there to be data. For example, the relationship could suddenly become curved below negative 20 degrees. The relationship could suddenly become curved or become non-existent above 70 degrees. So we logically don't do anything with that. We just say we limit our predictions to within the range of data. We interpolate within the line, and that's it. So, can we predict coffee sales for 40 degree days? Yes. We have data there. It's on a line. Easy. Can we predict for 80 degree days? No, because we do not have data all the way out at 80 degrees. We don't know what the line and the relationship might be, so we don't predict for it. Forecasting is a different world. So how do we use our line to predict coffee sales for a given temperature? Well, it's just like algebra. You pick the temperature you're interested in, and you plug it in for the temperature variable for x. So if I'm interested in a 40 degree day, I just plug in 40 degrees for the temperature, and then I do the math. So negative 553.7 times 40, that's subtracted from 49,337, gives us, on a 40-degree day, we expect on average to sell 27,189 coffees. Again, this is an expected average number of sales. You can do that with any temperature along the line. One other interesting thing here is this thing called the coefficient of determination, or the R-squared. There's a lot I could say about it. Let me just get to the point with it. When you take the correlation between two variables and square it, it becomes something called the coefficient of determination. In this case, when we take our correlation, which was about negative 0.7, and square it, we get an R-squared, or a correlation squared, of 0.549. This, for regression, has a very specific meaning. And the idea comes from this. Again, we've been doing all this stuff with relationships because things are varying. The idea is that coffee sales vary. The coffee sales are not the same every day. The coffee sales are not the same at every temperature. So these coffee sales vary, and they vary for a variety of reasons. One of those reasons we've tried to identify, and that's the change in temperature. So the question we ask is, because coffee sales vary, how much of this variation in coffee sales can be explained by the linear relationship with temperature? Bam! That's what the R-squared tells us. The R-squared is how much of the total variability in our response variable can be explained by this linear relationship, this linear regression on the explanatory variable. So, how do we interpret a coefficient of determination, an R-squared, of 0.549? We say that 54.9% of the variation in the coffees sold can be explained by the variation in temperature, or can be explained by the linear regression, or can be explained by the linear relationship with temperature. Those are different ways to frame it. But it's a very mechanical interpretation. It'll always be true, and it's a really powerful idea. So again, you take the correlation, you square it. You also get it by default from your statistics output, as you will see. But again, it's just the percentage of variation of the total variability in our coffee sales, a response variable that can be explained by variation in temperature. It's really powerful. Okay, so now our line makes predictions, right? But how good are those predictions? We're predicting average coffee sales. Are those predictions right to the actual data? How far away are they from the actual data? What's the error in the prediction? This is called the residual. The residual is the true value of your y variable at a particular point, the true number of coffee sales at a particular temperature, minus the predicted number of coffee sales that our line gives us. Again, it's the true number of coffee sales at a given temperature minus the predicted number of coffee sales at a given temperature. We call that a residual. The residual is just the difference between what the actual data are and what the predicted values are for our coffee sales. So it's the difference between the observed value and the predicted value. And in this case, we've identified some of these residuals on here. The residuals are just the distance between so let's see, what's this, like 15 degrees? So at 15 degrees, our residual is just this blue line right here. The difference between this actual data value here of around 55,000 and the predicted value around 45,000. And here, a negative residual. So again, this was a positive residual because the actual data value, y, coffee sales, 55,000, is larger than the predicted value of about 45,000. So it's positive residual. Our line underpredicted what the true number of coffee sales should be on average at that temperature. And here, our line overpredicted at this point. So the actual data point at around 40 degrees here for this specific case is about 20,000, and here it predicted something higher at about 35,000. We'll wrap up with the last video in just a sec. Thanks.